We actually now do know a fair bit. One of the people who's doing works in this area is Lutz Verschelt in Germany. Okay? Google for his name, you can pull up his papers. He's looking at variations between programmers. What's the effect of programming language on productivity? Oh, there's something the programmers argue about, right? What's the effect of different web programming frameworks was the study he most recently did. One of the interesting results, and I quoted this right at the start of Monday, productivity and reliability depend on the length of the program text. Putting it another way, regardless of the language or the level of the language you're using, assembly code all the way through to Lisp, most people will write roughly the same number of lines of working code per hour or per day. Okay? The difference, of course, is 200 lines of assembly code doesn't do nearly as much as 200 lines of Lisp. This is why I push you to use higher level languages. You're going to write the same volume of code per day, regardless of what language you're working in. That volume of code will do a lot more in MATLAB than it will in C. Now, sometimes that's not true. There are things that you can do in C that MATLAB deliberately prevents you from doing. Go and overwrite the buffer record for that audio device. All right? But take those things off the table. You want to be using the high-level language because it makes you more productive. How much you produce is constant. The multiplier due to the level of the language is what you get to change. That's a really interesting result, and that experiment has been replicated several times. Okay? So, here's another classic result. Barry Beam and all started this in the mid-1970s. This one has been replicated many times in many contexts. If I take a look at the life cycle of the project, where do most of the errors creep in? The ones that aren't caught right away? It's analysis and design. It's not coding. Okay? Most of the big mistakes are made in figuring out what the problem is, not in solving the problem. We often get a correct implementation of the wrong thing. Because this is a human communication problem. Once I know what to build, I can write the code. Figuring out what to build is the hard part, whether it's in a research context or in a commercial context. The other thing that's interesting, if I catch a bug here, it costs 1 unit of time to fix. This is analysis and design. If I catch it while I'm coding, it will cost 3 to 5 times more time to fix. If I pass it on to QA and they catch it and they have to feed things back to me, there's another factor of 3 to 5. So we're looking anywhere from 10 to 25 times more expensive than here. Right? Deployment, installation. Every phase in the project, the cost to fix the bug climbs by a factor of anywhere from 3 to 10. Okay? And those all multiply together. This really is an exponential curve, not exponential in the newscaster sense. Oh, we have an exponential problem here. Meaning big. Right? No, this really is an exponential curve. Every stage, we're multiplying the cost by anywhere from 3 to 10. Okay? This curve explains the two main approaches to software development. There are the pessimists, the big design up front people. Jackets, ties, deadlines, right? They say, if I tackle that hump in the curve, that's where most of the errors coming in, I'll put more effort into doing analysis and design so that I make fewer mistakes. All right? This is the assembly line approach. If most of the mistakes in the cars we ship are coming in when we put doors onto cars, let me go and look at how I can make fewer mistakes when I'm putting doors onto cars, right? You optimize the bottleneck. The optimists, the agile people, say, instead of doing one big cycle that lasts months, let me work in 1 week increments. Design a little, build a little, test a little, deploy a little. Repeat. Move a step. Course correction, move a step, course correction, and so forth. Right? Well, if I take that curve, shrink it down, and do lots of them like that, the total area under the curve, the total time I spend fixing bugs, is a lot less, isn't it? The area under that sawtooth is less than the area under that curve. So what this means is, these two groups have been yelling at each other for almost 15 years now. They're both right. They're just tackling different parts of the problem, and we've got empirical data to explain what we observe. Can we do both? can we simultaneously do more upfront design and shorter cycles? Well, okay, our data tells us that's where we should be looking.